So hi everyone. We're happy today to have first we have Kfir Blum from Observational Institute, and he's going to tell us about if quasar length in time delays can hint to a core component in halos instead of H0 time. So please, Kfir.
Okay. Thanks, Giovanni, very much for the opportunity to talk about this work. It's a very simple little point. I think 20 minutes are more than enough to explain it. This is work with Emanuele Castorina and Marco Simonovic. We started this when I was at CERN. Now I'm back at Weizmann Institute, and we're collaborating with my student, Luca Teodori. And there is another work in prep that I probably won't have time to mention, which is a little bit more complicated than the point that I will make here. But we'll see. Maybe if you ask questions, we'll get there. Yeah, so this is about the quasar lensing time delays that people are using to try to measure H0. I don't know if they hint to a core component in halos, but I doubt that they hint of an H0 tension. So that's, if you want, that's kind of my takeaway from this. But let's go through this. So to remind those of you who didn't keep very close watch on the situation of the measurements of H0, as of early last year at least, there was this tension that could be quite interesting. And in the camp of the measurements, the so-called late time measurements that kind of are in tension with the early type, with the SWIM-B or large-scale structural measurements. So in the same camp, there are the supernova type 1a measurements calibrated by something. For instance, this result I'm putting here. So there is an x-axis here, which is H0. And this range is the measurement from supernova type 1a, from one of the measurements from the RIS group calibrated by Cepheids. And this is probably the most well-known set of measurements that seem to hint of a tension. But apart from this set of measurements, there was, in fact, as of early 2020, another set of measurements that was completely independent and that actually had a nominal error bar that was very comparable to the supernova in kilometers per second per megaparsec, if I remember right. The supernova was 1.3 and this was 1.4. So it was the lowest error claim was 1.4. So it was very comparable. And these measurements come from strong lensing of galaxies by galaxies. From pictures like this one, where you see in the center, this orange patch is a massive elliptical galaxy, which is the lens. And in the back, you see 4 images of, so the bright spot is a quasar. And in addition to the quasar, you can see the arcs. They are real arcs. So you see the host galaxy that contains the quasar that is lensed. And images like this have been used by the TD-Cosmo collaboration. TD-Cosmo is actually a suite of, I think, 5 or 6 different sub-collaborations that join together and use these measurements to try to get H0. And what I will be talking about is really these lensing measurements. And so if I follow the history of this, in early 2020, we had this measurement, but then as time progressed, there was a revision of the measurement and there was an update by exactly the same group. And what happened was that the original measurement, the error bars inflated by a lot. This was late 2020 by Simon Birur et al. And actually in the same paper, when more data is included in the analysis, the error bars are still very large, but the central value actually drifts to the left. And now the latest update I'm aware of is essentially this. Central value sits smack on the Planck measurement, but the error bars are still big. Okay, so if you didn't know much about the lensing and all you really care about is H0, maybe you don't need right now to learn very much about the lensing anymore. However, this transition is curious and interesting, and I think my group had some role in what happened here, and I would like to discuss it, and also what we can really learn from these measurements. So what is my plan in the remaining probably 17 minutes? First, very quickly, for those of you who don't know, just recap how lensing measurements like this one actually try to measure edge knot, or how they measure edge knot. Second item is to show that actually they don't measure edge knot. And the third item is to try to discuss what do they measure, what can we learn from them. And I think with time, the lensing collaboration will progress in this direction and will eventually be focusing on measuring what I'll propose, but we will see. I could be wrong. Okay, so that's the plan. So a slightly busy slide, just to remind those of you who don't remember what these lensing measurements are. The lensing measurements, so first the TD Cosmo collaboration and the projects that are part of it are here. You can visit them, and all the credits for all of the experimental work is for them. I have nothing to do with it. But what do they actually do? Okay, so there are two types of observables that participate in this kind of lensing measurements. The first one is an extended source image. So this is an HST image. There are many pixels participating in this image of order 10 to the 4 pixels. Hundreds of them actually contain useful information, hundreds of these pixels. And these are information of the lensed host galaxy and the positions of the quasar images. Okay, so we have an extended source image, and what you can do with an extended source image, you can try to invert the lensing reconstruction problem, and you can try to figure out the surface mass density, sigma, of the lens. And you do it by solving the image reconstruction problem. What you're looking for is kappa, the convergence, which is just the surface mass density of the lens divided by the cosmological critical density. And it is related to the deflection angle alpha. So in the typical plot of lensing, right, we have the source, we have the observer and the lens, and there are two, in this case, 4 geodesics that are bent like that. And the deflection angle is this little alpha here. The true source angle is beta, that's where the source is, and theta is the angle where you actually see images happening. You're trying to invert this pixel map and get a handle on alpha, the deflection angle, which is a vector field on the plane of the image, and try to get from that also the lensing potential and the convergence. The model you're playing with is really the convergence. Now, from this story, you can measure again the convergence, the ratio of the surface density of the lens divided by critical density. If you're into cosmology, what you really want to measure is the cosmology. So you want to measure this factor here, the critical density, which is a certain combination of angular diameter distances. And so there is one extra angular diameter distance at the bottom. So this is sensitive to edge knot. Sigma critical is essentially proportional to edge knot. You would love to measure edge knot directly from this, but you can't. The reason you can't is that the cosmology enters here in the denominator, and up here in the numerator, there is the actual mass density of the lens, which you essentially never know to the few percent level that these collaborations want to try to do cosmology. But that's what you have for image. The second thing you have is time delays. So the pulsar is a variable in time. And so you get 4 delayed copies of the light curve from the pulsar. You can try to look for these delays. And so what you get is the following. You measure the time delays, the physical time delays, delta TAB between, for instance, image A and image B of the same pulsar. And then this physical time delay is proportional to a cosmological object, which is the time delay distance. It's this one here. Again, some combination of time delay distances. And this comes multiplied by a dimensionless factor, delta tau. And delta tau, again, if you have succeeded to solve the lensing reconstruction problem, then you have all of these angles. You have the source, you have a model for where the true source is, and you have the lensing potential. So you solve the first problem from the image. You get this factor, the dimensionless factor delta tau. You measure the physical time delay, take the ratio of these, and you get this cosmological factor. Okay, so you reconstruct the time delay distance, which is proportional to the inverse of H naught. That's how you measure H naught. And the cute thing is that this is a one-shot measurement. It's not a distance ladder measurement. The same system has the entire information to give you H naught by itself. So that's what these collaborations do, and that procedure essentially gave the original result for H naught that I was showing in the beginning by end 2019. Now, where is the devil in this? Or what's the problem? The problem is the mass screen degeneracy, or one of the key problems is this. And it's a very simple mathematical degeneracy, and it says that suppose that you have a model for the convergence kappa, or the surface mass density of your lens that solves the lensing reconstruction problem, and you measure time delay and you got H naught. The mass screen degeneracy tells you that there is an alternative model you could have come up with, which doesn't have kappa for the convergence, but it scales kappa by a factor and it adds an additive term to kappa. So it's a nonlinear transformation of this kappa, you just add a constant term. If you do that, and at the same time you rescale where you thought the source was, then the image information is completely unchanged. Magnification is changed, but you never know the absolute brightness of the source. But the pixel position, the image information is completely invariant. And so this is a degeneracy. Unfortunately, your inferred time delays, dimensionless time delays scale with a factor of lambda. So your inferred H naught would scale by a factor of lambda. Okay, so that's a major problem, because there is no way from imaging data alone that you can nail this kind of change in kappa. Now, obviously, the lensing collaborations are fully aware of this. This is known since Einstein, probably. And so they're trying to model it out in the analysis. And the way they've been trying to model this degeneracy out in the analysis is to ask, so where do we get this kind of mass screen from in physical life? It's not a physical mass screen sitting on some galaxy. That doesn't happen. So what you think is, you think that this can come from cosmological weak lensing, from matter along the line of sight between us and the galaxy and the source. Okay, so suppose our galaxy is sitting in some large-scale structure, cosmology, and so this line, there will be convergence and shear from this intervening structure. Collaborations try to calibrate this out using n-body simulations. And it's an important calibration. You can estimate how big this weak external convergence is. It acts very much like a mass screen degeneracy. The size of it is at the level of a few percent. So if you didn't correct for it, it would actually bias your H naught measurement by a few percent, potentially as much as 5 or 10% even. But they believe that they can correct for it. Now, whether they correct for it completely precisely or not, that's a very interesting question. I think it's not an easy problem to solve, but let us assume that they corrected for it precisely right, that's not the problem. Okay, there is a lot of discussion in the literature if they got it right or not. Let's assume they did. Problem is, even if they did, there is a residual mass screen degeneracy that they did not look at. Okay, and that's the discussion between internal versus external convergence, or internal versus external mass screen degeneracy. It's a very, very simple point. It's the following. So the mathematical MSD has talks about this kind of infinitely thin mass screen. Okay, but of course we are physicists. This is just an idealization, and so it's natural to ask yourself what happens if the screen is just not infinite, it's just big. Okay, so the scale of the screen extends beyond where the image information is. What then? Well, you can calculate, and the answer is, if the screen is not infinite but finite, you have an approximate mass screen degeneracy. It becomes very precise if the screen is large. A screen is not very physical, but if you take the screen and rotate it, then you realize that if you had just a diffuse, roughly constant core component in the total mass density of your lens, as long as you probe angles that are smaller than the radius of the core, once again, this has very much the effect of the mass screen degeneracy. It is an approximate mass screen degeneracy. And now this looks quite physical, and this could really happen in principle. You could worry that galaxies could really have this kind of core. So we play with this a little bit. It's very easy to see that the core is just an approximate mass screen degeneracy. In fact, I was kind of amused to figure this out in 2020, but actually back in 2013, this was already noted in a paragraph by it's hard for me to see, Schneider and Slew. So it was actually already noted in the past. I think people understood it, but for some reason the lensing collaborations didn't really pay attention to this. Is there a question?
Oh, no, sorry.
Okay, if there are questions, don't hesitate to stop me. Okay, so this is an approximate mass screen degeneracy, and it becomes as precise as I want if the radius is, if you let me have the radius big enough. Okay, and now you may want to worry about it. So how big does it actually need to be? If you look, for example, at some representative system out of the 7 systems that TD Cosmo and Holy Cow, the lensing collaborations looked at, for instance, this one, then I can plot for you what is the convergence profile of their best fit model. They use the pipeline, which has a power law model for the convergence. They got a very good reconstruction, a very good solution for the lensing reconstruction problem. This power law is very close in terms of 3D density to 1/r², as you would expect for galaxies that have roughly constant velocity dispersion. And this galaxy with the nominal pipeline, it gave this measurement, just the individual galaxy gave this measurement of H0. So how big does my core need to be if I want to add it to this model in order to solve the H0 tension? The answer is it's nothing. It can be very small. It can be a 10% correction. That's the dashed red line here. The dashed red line is just the convergence that you get if you MSD, mass screen transform, the original profile. You add a very little core and you rescale a little bit by 10%. And then you jump over here. Okay, so that's...
A quick question. Is these, including this, does it always go in the same, does it always have the same sign? Will it not always decrease when you include this? Or can you?
It didn't have to. So if what I do is to add the core, in terms of the original mass screen transformation, if my lambda is a little bit smaller than 1 minus lambda is a small positive number, and lambda is a number of order 1, that's 8.9 in this case.
Yeah.
Then what this will do, it would look like that, and it would decrease H0. However, you could entertain a negative 1 minus lambda, so lambda could be 1.1,
Yes.
which would mean that I have a depression instead of a core. Instead of adding a little core, I have a depression in the inner part. That's in principle totally possible, and it would take H0 to the opposite direction.
When you say it can be a very small core, what size core do you need to do this difference?
Thanks, Neta. So here I'm showing it. I'm just showing an actual example. So the radius of this core. Let's convert this to proper distances. These galaxies, these lens galaxies, sit at redshifts of order 1, half or 1, and most of the angular image information is around 1 arcsecond. So this is really a typical example, which is a few kiloparsec proper distance projected on the galaxy. It means that all these images, the Einstein angle is around a few kiloparsec. And this is a massive elliptical galaxy. my core has to go out at least a factor of few further out. Okay, so the critical, the characteristic radius of my core needs to be a factor of few further out. Here, a factor of 10 or so. So this core kind of peaks at a radius of a few tens of kiloparsecs. That's the radius. In terms of the mass budget, it can still be a small fraction of the total. Let's say that this profile is outside, is dark matter dominated. Let's suppose it's some NFW profile. Most of the mass could come from radii that are larger than a few, tens of kiloparsec. And so the total mass budget can still be totally dominated by the NFW. But in a certain region, the core can have some impact of order 1.
And is there any check on that from the kinematics, from the velocity, stellar velocities over that range? I mean, that's pretty big.
So we can discuss how big it is. So I have it in some backup slides, some discussions of it. I think there is a lot more to be done, but I'll comment more about it. But definitely kinematics, you can hope to use kinematics to resolve this ambiguity. For these type of lens galaxies that the collaborations have used, the kinematics data actually comes from a region that is quite comparable to the lensing data. So a few arc second effectively. And there the effect is very small. The effect is less than 10% and it's very hard to resolve. What you want to do, you want to get kinematics very far away and maybe find or exclude this idea. But I can comment about this more in the end. I think this may rule out eventually, or maybe detect this model, exactly kinematics. But I want to push this a little bit more. So what do we learn about galaxies if we actually add the CMB prior? So the point is just that, right? The lensing analysis has a degeneracy. This means that they cannot measure H0 without making some strong assumption on the profile of the lens. It seems natural to me. So at the same time, they have very precise measurement of something. And it seems natural, for me at least, that you will take this kind of very precise analysis and you will actually add the CMB prior on H0. If you want, you can add the supernova type 1A prior on H0. Add your favorite prior on H0 and ask yourself what I've learned about galaxies from these measurements. Because they are very precise, but what do they measure? If we go on with this game of the core, we can ask this question. And so if I do the same trick for all of the galaxies that the lensing collaborations looked at, that's the table here, I find that to make all of them agree with H0, all of them have to have a picture that is rather similar to this one. They need to have a core component which adds a convergent correction of about 10%. It means that at a few kiloparsec from the center, the proper distance center of these galaxies, there is a diffuse core component that makes up around 10% of the mass of the system. That's what it would mean if this was reality. And I'll skip this quickly, but we can check this with the mock. So that's an example with Luca, my student, that we did some mocks to check. And the point is as follows. So suppose I take the nominal pipeline of the lensing collaboration, which is, for example, an elliptic power law model for the lens. And I simulate a truth configuration that actually has this kind of core, this kind of 10% core. It has a truth H0 that is precisely in agreement with the CMB. What will it converge on? So their model will converge on a wrong H0. It will converge because their model does not include the core component. It will actually converge and tell you that you've measured H0, which is 10% larger. Because what the model does, it automatically finds the MSD transformation of the truth that reproduces the imaging data. So it actually gives a pretty precise but inaccurate measurement of H0. If I would take their pipeline and I would actually allow the freedom for galaxy to have this kind of subdominant core component, what will happen is, you can see it here, what will happen is that naturally there is going to be a very strong degeneracy between H0 and the convergence of the core, so the core component here. And if you look at the measurement of H naught, it's very poor. You will not be able to measure H naught. You'll have very large error bars. If I do the next step and I actually impose a CMB prior, for instance, from Planck, or H naught prior, for instance, from Planck, then in fact, we can actually measure with this prior, we can measure the core component very well. So, or the model which has the core will converge and will give you a result that is a very good measurement. You can actually, your measurement or your evidence for a core is comparable to your resolution of the prior on H naught. You can reach a couple of sigma per system from these 6 or 7 holy cow systems. So maybe that's what they've seen. I don't know, but maybe that's at least a logical possibility. And the collaboration was very responsive to this comment that we had. And so in 2020, that's the update that I showed in the beginning. They actually took this kind of core component and put it in the pipeline and rerun the pipeline on the data. Simon Beer did it in this paper, and that's what they find. That's the update that I showed you about. And what happened is that the error bars inflated by a lot. So if you add that core component, just with the original systems, your error bars inflate. So the central value stayed 74 for H naught, but the error bars inflated by a factor of few. So before it was 74 plus minus 1.4 or something. Now it's 74 plus minus 6. The error bars inflate very much like I was proposing in the mock. However, in the same analysis, they also added a blind analysis of around 30 additional galaxies which had kinematics data. And when they did that, so those extra galaxies have kinematics data, but they don't have time delays. They just constrain what you think is a good guess for the profile of the galaxies, just imaging. Then what happened that the central value, when you added kinematics, like Neta asked, the central value actually shift the CMB. So it looks like with kinematics, these ellipticals actually want to have a little core component. And if you compare what the collaboration finds without H naught prior for this core convergence, it's very consistent with what we were guessing. Now that would be great if I only believed it, but to be fully honest, I don't fully believe it. I think they took a slightly dangerous shortcut in the way they implemented the kinematics likelihood. And I think it should have been done a little bit different, since this entire hint, positive hint for a core, comes from kinematics.
Is it us? No, I think I have internet.
Okay.
I think it's moving.
Did you lose me?
So, sorry, yeah, we missed you here.
Okay. How much time do I have, by the way? I'm essentially done. Am I over time?
No, no. It's fine if you talk a bit, like for a few 2 minutes, 3 minutes. It's totally okay.
That's more than enough. Okay,
We should really finish on time though, Giovanni.
Yeah.
Sorry?
We should finish on time.
Yeah.
We finish on
okay. 1 minute. I'll take 1 minute and I'll finish. So that ends what I promised in the beginning. These lensing collaborations, or the cosmography measurements, are subject to mass screen degeneracy. The latest analysis, this is the result. The big error bar is the big news, not necessarily the central value. The error bar is big because now they really allow for mass screen degeneracy. So I'll skip these comments. The comments just in less than 1 minute. These cores look non-minimal. Why would galaxies look like, not like, say, simple power laws? That's what the collaboration has been asking me. Why are galaxies? Why wouldn't the galaxies be just minimal power laws? Why do I want to add this core component? It's non-minimal. I totally agree that it's non-minimal. and it's ad hoc. I had no original motivation, I think, or no good motivation to propose it, but why not? Why should it be minimal? And I can actually think of several reasons in which these kind of structures will actually be there. For example, ultra-light dark matter, a small component of order 10% of ultra-light dark matter, if just a fraction of dark matter is some very light axion, we more or less understand by now that it would tend to produce these kind of diffuse core structures. It's allowed by all cosmological constraints, and it would actually try to converge as roughly the correct density to make this effect. So this is just a proof of concept that it's not hard to come up with ideas that galaxies could actually have this little feature, and it's interesting to look for it. Okay, so I'm done. I just leave you with a summary, and if you have time and you want, we can discuss. If not, I think I'm done.
Thanks a lot, Kfir, for so are there some questions for Kfir?
Yeah, can there be some more prosaic explanation to this core? Can it be some like baryonic physics, not necessarily dark matter?
Oh, I don't know. Maybe yes. I don't know. I think it's if I need to really guess, if you work hard enough, you may find something with baryonic physics. But I do need to stress the proper distance is a few tens of kiloparsec. You know where this feature has to extend to. If you go too far, then all of the mass is in the core. If it would extend too much, it would win over the NFW by a lot. That I think would be extreme and probably in trouble with general weak lensing analysis and maybe even kinematics. But this kind of small feature, maybe it's something very prosaic. I think it could be.
But how much mass is there in this core? If I didn't make this.
Right. So what we really know, if this is the answer for the lensing edge knot tension, then around 10% of the mass is in this core in the region where right now there is information. However, there is no reason for it, and we know that it extends far beyond that point, at least a factor of 2 or 3 in radius beyond the few kiloparsec region. So by the time it does that, because the background density falls down roughly like 1/r squared, this core eventually catches up and it becomes an order 1. So if I need to guess, this thing is an order 1, at least several tens of % effect at a few tens kiloparsec. So I can show you, for example, how we would look in the Milky Way.
In terms of the total mass, I mean, if I had to rearrange the mass inside and move some stuff out somehow, how much
You-
does that have to? Tens of % or just a few %?
Tens of %.
Okay.
I
So-
don't know if you're moving it, yeah, from inside out, from outside in, what exactly you're doing, but that's the ballpark.
So Kfir, if we look at other galaxies, not specifically these lens galaxies, but other comparable galaxies, isn't there evidence for or against from kinematics or
So-
from lensing because it's such a large core in scale, in physical scale?
Right.
I would think that there is some evidence either for or against such a large core.
So if there is, I don't know about it. The nearest to this that I found was in fact for massive ellipticals, so kinematics analysis by this group for massive ellipticals. But the radius is big, but the effect is small, at least as far as edge knot tension is involved. So in the plot, what I'm showing is the 3D density model as a function of radius for one of the galaxies that are considered. There are some others, but the picture is very similar. The green band, very roughly, is the uncertainty range for the models they consider. And the blue line is what you would need to completely solve the edge knot tension for a galaxy like this. And the red dashed line is highly, exaggerated case. So it would shift edge knot by 25%. There is no way that this is life, even from cosmology, right? But the blue line is what you would need. Given that this analysis, and actually all analysis I'm aware of, didn't explicitly look for a core, And given that they have auxiliary parameters related to anisotropy, I think this would be allowed. But I also think it's very interesting to try to look for it.
I have a question.
Sorry,
In terms of words that you're using or terminology.
Sorry, maybe
what you're talking about is not a core, really. It's more like a diffuse, extended, finite size component. Because your inner region, if I'm not mistaken, right, your inner region is still very cuspy, right? So
definitely, yes.
So you don't have a core in the, the people use core in different contexts, like for dwarf galaxies.
I know. Yeah, I'm sorry if this is confusing. What you're saying is precisely right. So in this example, or in general, the black line here would be the total density. It's a cusp in the inner part, at least where the imaging data is concerned. That core is a very subdominant component in the inner part. So I call it a core component. There is a diffuse component. The point is that the MSD is a little bit unique, right? I mean, you're allowed to scale your overall density profile and add something that is roughly a constant. This is why I think that maybe the picture is roughly like this. That would be the correct statement.
In the context of galaxies, I'm not sure about elliptical galaxies, but in context of spirals, you very often have broken power laws. Like two power laws, one internal power law and one external power law. Because the stellar halo, for example, on large distances is assembled slightly differently than the inner region. So you might want to try also this, right? Instead of having one power law, you just have two power laws and a transition radius.
Thanks. So I think, let me generalize this. I think that the message is these lensing collaborations needs to consider wide priors for what they think the profile of galaxies are. I took the most evil possible option, which is a mass screen transformation. Maybe the answer is something more modest, just something, something smoothly falling, but slower than NFW. And you want to slightly play with that. That could be. It hasn't been done. I think not enough. The bottom line is that you want to use these measurements to constrain the structure of galaxies and not necessarily to get H0, I think. This core is an extreme, just an extreme, the cleanest example.
Okay, so we are already a bit over time, so maybe we can thank Kfir again for the very nice talk.
Thanks very much.
And we can move to Cyril
yes.
from Johns Hopkins. I think you are already online.
Yep. Let me put on the share.
I think you should be able to. Yeah, I think. So Cyril, you can tell us about AGN variability and HEAN in the age of VRO. So I don't know any of those.
Yes, exactly. Oh, well, perfect. Thank you so much. So just to give a little bit of background on myself, name is Cyril, 5th-year graduate student working with Mark Jankowski at Johns Hopkins University. And I've done some work on the CMB intensity mapping neutrinos, and it's kind of all somehow led me to start to do some work on AGN variability. I also tying that in together with high energy astrophysical neutrinos, or HEAN. And so that's what I would like to talk to you all about, AGN variability and HEAN in the age of VRO. And so the natural first set of questions would then be, what are AGN and how do they vary? And as depicted in this cartoon, an active galactic nucleus, or AGN, is composed of some extremely massive compact object, an accretion disk, and a very bright jet that runs parallel to its angular momentum vector. Not depicted in this cartoon is a region surrounding the accretion disk, where a bunch of dust in the shape of a torus, aptly named the dust torus, scales out to some number of parsec. Moreover, in between the dust torus and the accretion disk, there is a somewhat unknown region of ionized dust that emits broad lines of optical and UV light called the broad line region. AGN variability refers to the observation that the intensity of most AGN varies on time scales from minutes to decades and frequency bands ranging from radio to gamma ray. For example, on the figure to the right, you can see the optical light curve for NGC 5548 from late 1988 to late 1996. So that's about 8 years or so. From this picture, we can infer that NGC 5548 shows almost no variability on timescales shorter than a few days. But as you scale out to timescales that are on weeks, months, or years, significant variations can be seen. While NGC 5548 is only a single AGN, most AGN are observed to show similar trends with variability. And to date, most success in describing AGN variability has come from the description of the stochastic nature of such light curves. That is, most AGN light curves can be described by a random walk that reverts to its mean. And NGC 5548 sort of follows this idea. As you can see, its light curve kind of jostle around randomly, rise and fall, but never stray too far away from a mean value of about 7.5 or so. Mean reverting random walks are more formally called damped random walks, and their modeling only requires two inputs, the amplitude of variation A and their mean variability timescale T bar. To date, no definitive causes of AGN variability have been identified, and even the relationship between AGN parameters and their observed variability is unknown. This mystery has primarily been because previous analyses of AGN variability have been limited due to either small AGN sample size or infrequent visit times. And both of these will be remedied with the dawn of VRO. And so you then ask, what is VRO? The Vera Rubin Observatory, also known as VRO and formerly as LSST, is an astronomical observatory currently under construction in Chile with first light slated for the end of 2022, so next year. It will observe the electromagnetic spectrum from 320 to 1080 nanometers in 5 frequency bands, UGRIZY or UGRIZY for short, and cover the entire southern sky, or half of the full sky. It has a pixel size of about 0.2 arcsec, with each pixel able to detect objects as faint as 25 mags at 5 sigma. As a result, VRO will measure the flux of over 10 million AGN. Moreover, each band will be visited a different number of times over the full course of the 10-year survey. And if each band's information can be compiled into one data point, then each pixel will be visited about every 3.5 or so days. So what I mean there is, you have each band, the U band there is going to be visited 70 days, G 100, so on and so forth. If I take 10 years and I divide it by the sum of all those numbers, I will get that I will visit each pixel about, and therefore each AGN every 3.5 days or so. With the huge number of sources, coupled with a vast increase in the number of regular high frequency observation epochs, VRO will allow for unparalleled precision in variability analyses. And so what I sought out to do with this work was to quantify this precision for a single AGN and for the full population of VRO AGN, so that we can start to gain a handle on the ability of VRO to be used in variability studies. In order to do this quantification, I performed an expected information analysis as a standard and found the following VRO sensitivities for the variability amplitude and timescale. First, I show the covariance for such measurements of a single AGNJ with apparent magnitude 22.3, which corresponds to the mean apparent magnitude in VRO's I band. Remember, the I band is one of the 5 frequency bands, UGRIZY. The x-axis is the variability amplitude A sub ji of this AGNJ in the band I, and the y-axis, the variability timescale T of the same AGN. For each of these subplots, I show fiducial parameters for the covariance. So the variability amplitude goes from 0.01 to 1, and the timescale from 3 days to about a year. And so the way you would read this is that you go, let's say, to the bottom right-hand corner. That would depict the covariance between an AGN with amplitude equal to 1 and timescale equal to 3. The black circles indicate the 1 sigma or 68% confidence intervals, and the yellow, the 2 sigma, 95%. And I should note that even though that this was done for a single AGN with a specific magnitude of 22.3, these results hold for pretty much all magnitudes that will be observed by VRO and all frequency bands, primarily because we are not we're not limited by incidental noise or photometric error, or if I put my cosmologist hat on, it's in the cosmic variance limit. And from this plot, I can therefore conclude that AGN in VRO will be able to be separated into up to 10 timescale correlation bins. And so how I do that is, I go back to the bottom right-hand corner and say, here I can measure between 2.5 and 3.5, and then I would go to the next bin, let's say around 5, and say what the error is there, and I would continue stacking all the way up until I have enough bins that cover the entire observational space, and I would see I could do up to about 10 of these or so, which is much better than a 1 or so before. So that's for a single AGN, and I can now show the covariance for such measurements of the entire VRO AGN population, assuming the following relationship between luminosity, redshift, and the variability parameters. So in this case, the variability amplitude is taken to be constant for each AGN. We just chose that ad hoc. And the variability, or the observed variability timescale, goes as a power law on the bolometric luminosity of the AGN to some power with index beta. The subscript B indicates the particular band of observation. And what you might notice here is that now I have superscripts that are R and O. This is only due to the fact that there's going to be a relationship between the rest frame variability and the observed frame due to cosmological redshifting. And therefore, we include the factor of 1 plus Z to account for that. The x-axis here is the index, and the y, the x-axis is the percent difference. So for each of these, I plot beta minus a fiducial value divided by that quantity, divided by the fiducial value, and the y-axis, the analogous quantity for the rest frame. So the fiducial values are listed again at the bottom for the index, ranging from 0.1 to 0.5, and then for the y-axis, it's just done for 30 and 100. I don't do it for as many values of the time scale, primarily because the plot doesn't really change that much. It sticks to the same. And what you can see again is that black circles indicate 1 sigma 68, yellow 2 sigma 95, not limited by photometric error, so on and so forth. And since increases in the rest frame norm T sub BR and the index beta both increase the observed variability, they are anti-correlated, as shown in the figures. And what I can then glean from looking at this plot is that, a power law relationship between the luminosity and redshift and the observed variability would be able to measure at best to 1 part in 100,000. So that's a pretty great optimistic result. If I compare, there was a recent paper that sort of did a similar analysis linking the size of a black hole to its observed variability and found, I think, the results to be 1 part in 10 or so. So this is much better if done all properly, and so on and so forth. So together with these 2 plots, these results suggest that with VRO, precisely measured variability parameters will start to take their place alongside spectroscopy in the detailed characterization of individual AGN and in the study of AGN population statistics. So moreover, what you can also take from this is they say that, if I have such precise measurements, maybe I can start using AGN variability as a thing with other analyses, And so this sort of leads me to the second part of the talk, where I'll be talking about high energy astrophysical neutrinos. And I, again, start with the basic question, what are high energy astrophysical neutrinos? In 2013, IceCube detected a now 7 sigma discrepancy between the observed neutrino energy spectrum and that of the modeled energy spectrum of atmospheric neutrinos, so neutrinos that arise from cosmic ray interactions with the Earth's atmosphere. Atmospheric neutrinos were expected to only contribute up to 26 or so events, and IceCube saw 54. Once you take out these atmospheric events, what neutrinos are left over are termed astrophysical in nature, and still today we don't know what sources the majority of them. However, we do know a few things. So on the figure to the right, I show the total neutrino flavor differential energy flux against the neutrino energy in GeV. The black crosshairs are the best fitted data points. The dashed line, a single power law fit. The red region, the 1 sigma error on this fit, and the dark red region in particular, the observable region for astrophysical neutrinos. So from the most recent IceCube results, we can then take away 3 things that describe HEAN. 1, they are observed between energies of 10 to the 4 GeV and 10 to the 6 GeV. 2, they approximately follow a power law with spectral index 2.53. And finally, their flux normalization is order unity. Now, while these are the main characterizations for this isotropic source of neutrinos, a few years ago we got a hint to when they sourced them. In 2017, IceCube and Fermi detected a neutrino coincident with high blazar gamma ray activity, thus confirming suspicions that blazars, or more generally AGN, may be a possible source for the bulk of astrophysical neutrinos. Follow-up studies have capped this contribution to about 15–20% or so. And so alternative classes of AGN that are not as bright, such as radio galaxies and whatnot, must be considered. A more exotic explanation and more unlikely but fun nonetheless is that possibly cosmic strings source these neutrinos. I'll first talk about the possibility and entertain the idea that AGN source HEAN, and if I have time, which I most likely will not, and so please just ask me questions about it later, the idea that cosmic strings do it. As a quick overview, there are 2 avenues by which AGN are theorized to produce high-energy astrophysical neutrinos. The first method of neutrino production is the emission of cosmic ray protons, which then interact with soft photons to produce mesons, and in particular pions. And this method of production is called photohedronic, the photons obviously being depicted by the squiggly lines. The second method of emission is when these cosmic ray protons instead interact with nuclei in the clouds of dust in, say, the broad-line region or the dusty torus, and therefore again produce mesons, in particular pions. In both cases, pions then decay into gamma rays and some neutrinos via the processes shown at the bottom. Now I want to discuss how to contribute, characterize the AGN contribution to high-energy astrophysical neutrinos. So remember, blazars and other high-intensity AGN can't contribute to the entire HEAN background since they have been capped at about 15% or so, and so it must be less bright AGN. Since any given AGN is not that bright, you have to do a population analysis. Therefore, what I and collaborators have proposed to use VRO to measure the intensity catalog of the 10 million or so AGN, which is a 10-time improvement over the previous catalog from SDSS. But you can't just have AGN intensities in this case. You have to have something to measure the neutrinos. And so in conjunction with this, we propose to add measurements from IceCube, Baikal GVD, and KM3net. So IceCube, I think we are most likely all familiar with. It's been going on for about a decade or so now. Baikal GVD and KM3net are similar generation neutrino observatories as IceCube. They've just been sort of delayed, and they're going to be coming in full operation online within the next few years or so. They have the same neutrino collection area, and so together with IceCube, they have 3 times the collection rate. However, Baikal GVD and KM3net are both located in fresh water and have much better angular precision, twice the angular precision over IceCube. If you want a little trivia quiz fact, apparently Baikal GVD is located in a lake in Russia, which is the deepest and largest freshwater lake in the world. So it holds, I think, it's like probably the size of what, Belgium or something. It's fun. But with these two large data sets that are going to be coming online, it's natural to propose a cross correlation between these two sets to determine how many high energy astrophysical neutrinos come from AGN in this catalog. So how are we going to, what type of cross correlations am I talking about in particular? So there's going to be a temporal one and a spatial one. So let's begin with the temporal. So here I show, well, on the x-axis is time and the y-axis is variability. So by variability, I'm talking about the intensity of the AGN, subtract out the mean, divide by the mean. And the black curve sort of shows the cartoon of a light curve of an AGN over time. And the orange arrows indicate, well, their location indicates the neutrino event arrival, and their height indicates the value of the variability at the neutrino arrival time. And so your null hypothesis would be that, you know, if neutrinos have nothing to do with AGN or so, if I took all of the values of the variability at the neutrino arrival times, I summed them all up, I would get 0. That's your null hypothesis. And therefore, any deviation from 0 would indicate some form of signal. And that would be your temporal way of cross-correlating. In addition to a temporal component, you also have a spatial component. The spatial component somewhat goes along the same way. You know, in a standard scenario, a neutrino comes from an AGN and does not interact with anything along its geodesic and just comes to us. And therefore, you would expect that aside from its angular error, it would match up where the AGN came from. And that's sort of how the first detection of the Fermi and ice cube went. You know, we saw essentially the neutrino was overlapping with the AGN. And so we were like, it came from that. But here in this case, the orange circles are the neutrinos, and the black circles surrounding that, the angular error of ice cube, CAM3net, take your pick. And the small little blue circles are the AGN in the background. And so you would want to see if there is any deviation from an isotropic signal, because if they have nothing to do with one another, then you would expect some overlap number. But if they start to, you know, happen to overlap with an AGN, you would have a bit more of a signal than your isotropic case. So these are your two methods of cross-correlating to gain information about whether AGN contribute to HEAN. And so what then is our prospects for—
The size of the ellipse again is what?
These are about 0.4 degrees and then 0.2 for CAM3net and Baikal GVD.
So this is the localization of the—
Yes, yes. So what can we then say about measuring the AGN contribution to HEAN? Well, here's on the x-axis the neutrino fraction that comes from HEAN from the VRO catalog, and the y-axis the SNR with which you can measure this fraction F. The blue, light blue curve indicates the SNR with only using spatial data alone. And now the green curve is the simultaneous use of temporal and spatial data. Now, you may be surprised when looking at this at first glance, because you see that when I have time and space, all of a sudden the curve decreases. And what you may naively say that, oh, I expect that using them both, they're supposed to be larger. But one has to remember that this detection of the simultaneous temporal and spatial uses the fact that neutrino emission is somehow related to variability. And therefore, establishing a connection between variability and neutrino emission is intrinsically linked to the amplitude of said variability. So if variability is small, then it's much harder to make this connection than if the variability was large. Now, so that's what accounts for the difference between the size of the spatial and when you do a simultaneous temporal and spatial. Now, under the null hypothesis, though, these two methods can be combined together to get a full, and so you get a red curve when you actually add those two, and that would be your expected result. Now, clearly, most of the information comes from spatial, and spatial can go down to about at least 1 sigma, down to a 3 or 4%. But at 3 sigma, you can even detect contributions to the background of order 10% or so. But even though I said that simultaneously temporal and spatial are a bit larger, in fraction at least, and smaller in SNR, it's not so small that you wouldn't be able to infer anything about characterizing temporal information of neutrino emission and variability. Because at 1 sigma, you just need a contribution of 10% or so to actually yield 1 sigma detection. And this sort of means that, maybe possibly within this coming decade, we can start to actually further characterize what actually produces neutrinos in AGN if AGN are detected. And since they're the most promising candidate and whatnot, the fact that we're observing the half of the sky and, we're having these 10 million AGN, I would say it is fairly likely that we're going to see more than a contribution of 3%, 4% from AGN in the next decade. So this is a nice thing to see. Yeah, and that's how I would say my takeaway is from here. I'll say just a few things on future directions. I'll skip all the cosmic string stuff. So some things which you may be able to do with all this stuff. I mentioned that AGN variability could be used as a tool. What about it as a cosmological tool? So I mentioned a power law between bolometric luminosity and observed variability. So maybe you could get, if you measure observed variability, you can then infer the bolometric luminosity. You have the flux, then maybe you can measure H0. Who knows? It could be plagued by other systematics and whatnot, but it is a thing I think worth exploring given the fact that you have such a large sample of AGN that could maybe drive down the error of any type of particular measurement. Second of all, if you have high energy astrophysical neutrinos, there are some assumptions that were made in that analysis. For example, we assumed that the time delay between AGN and neutrino were signals were 0. That doesn't have to be the case. And possibly if you have a time delay, you can maybe infer information about where in an AGN a neutrino is being produced, because the frequency of the AGN is sort of related to the location from the center of the AGN. So higher frequencies tend to be produced more in the central component and longer wavelengths at further out.
So this is a time delay between what?
Optical light curves and neutrino events.
Okay.
Yes. So possibly if you know that optical tends to come from let's say the broadline region, for example, and you see a neutrino time delay, then maybe, and if they exactly match and you observe no time delay, then maybe you might infer they're maybe being produced in the broadline region, for example. There are the other degeneracies and whatnot, but let's take it as like a guesstimate. And therefore, if you know it's being produced in the broadline region, maybe you'd be able to then further rule out models of other types of neutrino production and so on and so forth. Other things you could do are involve nonlinear relationships between the luminosity and the neutrino event. So that would incorporate higher order correlation functions and whatnot, but whatever. And lastly, what about as a dark matter detection? There's still some, if the fraction is large enough and the SNR is large enough, maybe you can then start to use the correlation as like a tool to discriminate from alternative scenarios. In particular, I said the neutrinos have to travel along a geodesic without interacting with anything, but if neutrinos self-interact, then they would possibly interact with the cosmic neutrino background, thus spoiling temporal and spatial correlations that would be present otherwise. And then if neutrinos interact with cold dark matter, then also you would have some similar type of spoiling occurring. So just possible things you could do moving forward and that I'm interested in having in the back of my head. Definitely ask me about also cosmic strings and primordial magnetic fields if you want to talk about that too. But that's all I have for today.
Cyril, actually, I think maybe amazing shortening a bit your talk. It was.
Yes.
Thanks. Sorry.
No worries.
Other questions for Cyril?
I have a question that so we've got quite excited about the fact that we should get close to 100,000 AGN variable AGN through like millimeter observations with like CMB experiments that see them. But you just told us you're going to get 10 million. So now I feel a bit like, 100,000 was exciting, but is it? So would 100,000 millimeter AGN with their variabilities add to this thing, or will the optical just kind of sweep it away with the millimeter?
So I think having additional data in different frequency bands is definitely useful because different foregrounds are present. You could, and it also depends on what questions you want to ask. For the neutrino thing, it's actually wonderful because if you have, as I said before, information in different frequencies, you can get more information about time delays. So I think that's great. For just the variability studies, and if you just talk about, okay, a couple of things. One, variability changes in different frequency bands. So you also want to know about how variability is occurring in another frequency band because we don't know what actually causes the variability. For example, you could have that there's the X-ray reprocessing from the inner core that goes out to the broadline and dust torus that then re-emits at lower frequencies. But then you could also have an intrinsic component. And so having a different frequency spectrum might be able to aid in distinguishing between those two scenarios if you compare it to if you just only had optical data.
Yeah. Thanks.
Are there other questions for Cyril? You will be here also today, you said,
yes.
No? For
yep.
Okay.
Yeah.
So, well, I have one, but if I will maybe quickly ask, I don't know if can I ask a super quick question or 1 minute maybe? Let's just, can you elaborate a bit more on what you said about the cosmic neutrino background? What was the signature that you were talking?
The cosmic neutrino background.
Yeah,
so if you have self-interactions between neutrinos, then if you have a high energy neutrino, then it could scatter off of the cosmic neutrino background. Now, if I have temporal let's say surmise that the optical signal of light and the neutrinos have 0 time delay. Then if I have scattering off of the neutrino background, that will make a non-zero time delay.
Okay.
Now, I don't know what the hypothesis prediction or what the model prediction would be, but there's going to be something there.
Okay.